Okay, so let us begin. So last time we finally got to defining our main objects, meaning smooth points and singularities. So I'll just recall the quick definition. So we had, so this was a local problem. So this is why I took mainly an affine variety, and I took a point on X, and I said that A is smooth. I'm just recalling some vocabulary. So it was smooth, regular, or non-singular. So, if and only if we saw that we had the Jacobi criterion, we said that the rank of the matrix is bigger than n minus the codimension at A, and I of x and the Fi's are just generator of the idea. And we saw a more algebraic definition which said that the dimension of the local ring is equal to the dimension of the quotient of this first quotient of powers of the maximum. Okay. So this was the achievement. So last time. Today we are going to explore and just push the consequences of these notions further along, and we will try to see something more algebraic. So last week was a rather geometric lecture. Today it's going to be a lot more algebraic. Okay. Okay, so one of the things I wanted to talk about today was the analytic intuition. Now, if you look at the Jacobi criterion, you probably have already encountered it in differential geometry, because it gives you the preliminary conditions, the premises of the implicit function theorem. It's the premise of the IT, and not anything. The implicit function. So, what does it mean? It means that if the base field is R or C, whether you're working in differential geometry or analytic geometry, then locally around A on X, X is given by the graph of a smooth function, smooth map. Okay, so this gives us a little bit the close approximation of the IFT. But as you know, in algebra you can't really have an IFT. In order to give rather sophisticated context for the implicit function theorem, you need to go to Hengelian rings. That is very complicated and beyond what this is meant for. However, this gave us a little bit of an intuition. So we wanted to find algebraic structures. So where we could apply, where we could apply fixed point type theorems. At least this gave the impetus to find structures where we can apply fixed point theorems. This gave us completions. So let's talk a bit about completions. First, I'll give you the general definition. Okay. So how do they frame it? Okay. For a ring A and ideal I of A, define the I-adic completion. So, what is the list? So there are no notations for indicating that we are doing it with according to I. So sometimes we use this notation, but it is misleading because this could mean, the power of construction. But so this is why usually we just use that. Okay. So what is this? This is the projective limit of, so beginning with 0 if you want, of these quotients like this. And don't worry, I'm going to explain what this construction is. So these are made of sequences, modulo I to the power n in the product space like this. So for each of the factors a divided by in, I take xn, I take an element, modulo xn, and the requirement for these elements is that they are coherent from one to the next. Right? For like that. So if this looks a little bit too abstract, which I understand, I'll give an example just later on, but for a local ring, so usually the local ring is noted with the ring and its maximal ideal. Sometimes we even note the residue field. It's, let's say, implicit completion. Its completion is taken for I maximum ideal. So this is why, since we are going to deal a lot with the local rings, which are local rings, then when we mean by the completion of this ring is just completion with respect to its canonical maximum. So let's give some examples. So the most simple example we know is the ring of polynomials. It's statement, let's say. And the ideal that we generally take is just the maximal ideal around 0, let's say. Well, its completion, you maybe have heard of it, is the power series ring. Like this. And actually, the theorem I wanted to mention today, at least as a first result, tells us that for regular varieties, the completions of local rings are never more complicated than this. So let's state this theorem. So this is why I mentioned this analytic intuition, is that if we use this completion process, then we arrive at something even closer to the the differential geometry picture. So the theorem is called the Cohen's structure theorem. In fact, well, I should mention for varieties, but the term is a lot stronger in a more general case. Our specific case is simple because we have a base field which allows us to say that we have a local ring which is equally characteristic. So, what is this? Let me say it. If I have a regular point on a variety, let's say dimension C, B, yeah. Then let's say there are isomorphisms. So how do we build? So we take our local ring, okay, and there is always a canonical morphism towards its completion. It's canonical completion. I just take an element x, and I just take x mod in, x mod in plus 1, and so on and so on. Okay. But the really interesting part is the fact that this here is actually isomorphic to a formal power series ring. And in fact, we can even give a more precise idea of what's going on here beneath. I just need to take, so I just need to take local coordinates here, and I just associate the powers here. Right? Oh, maybe the B double, like this. So we even have an explicit form of what this is. So this is why generally formal completions of these rings are not that different from very simple objects here. And this is why studying the completions of singular points is a rather more complicated endeavor, at least to my knowledge. Okay, so let's give a, let's see, do I have,
This over ICMS-Sofia, this bracket, the internal bracket here, this means that these are not polynomials but rational.
No.
Continuous polynomials.
No, what I just meant is that the local coordinate Ti is sent to xi.
No, what he asks is that
power series.
Yeah,
Power
these are
series.
infinite series.
Okay.
Oh yeah. These are infinite series. So if you want, yeah, I didn't really define them. I kind of assumed you'd know what they are, but yeah, it's not necessarily obvious to everyone. So. So 1, xn, n, and so these are elements with this for IAs positive, and there's no restriction on the AIs. They can be non-zero for an infinite amount. This is what power series rings are. And you define
positive, not negative, no fractions. Only
no, positive.
Okay.
Positive, yeah. So if you want negatives, a finite amount of negatives, then you have Laurent power series. But yeah, forget it. Oh, okay. So Let's see. Well, I could give a small proof of this. One of the other parts of this thing is that here is an inclusion. So I'm just going to sketch the proof. So let's see, we have two parts here. One is let's see, Kuhl's intersection theorem. Right? Basically, the kernel of morphism 1 is the intersection of the different k's, and this is 0 by Kuhl's intersection theorem. This is the first idea. The second idea, we first show that there's how do you call this? A subjective morphism from the right to the left. So we start with phi. And it's kind of the reverse idea of what's going on here. We assign to each coordinate monomial the local coordinate, and then we want to see what's going on the successive quotients. Well, yeah, I kind of phrased it, but in the conclusion transformation. Okay, so the main idea is to see that if I want, let's see, how do I close this? Yeah. But this may not be subjective, right? You might have a lot more complexity around the residue field, for instance. But what you do know is that the discrepancy will be infinitely small. Wait, actually, you can find discrepancy here for an ideal M, which is going to be So you can take an element in your X A and you can approximate it by a polynomial expression in the local coordinates by essentially trying to find its Taylor expansion. And what's the remainder of this Taylor expansion looks like something like this: the remainder of the maximal idea of polynomials and something inside of the maximal idea with a higher power. So this kind of looks like Taylor-Lagrange theorem for power series, well, approximation theorem. Okay. Thus, you can use phi, uses the surjective morphism from polynomials. So surjective morphism is written like this sometimes. Okay. And this, if you take let's say, product of all these morphisms and you take the projective limit, they can assemble, all these morphisms assemble into the completion morphism between the two. This is just roughly a sketch, and this will be a subjective morphism. And to show that it's injective, if not, then there's going to be a problem with the dimensions. So, then the dimension of all x a, which is going to be the dimension of all x a, this is one of the features of completions, which is going to be d. Well, it's going to be less strictly than the dimension here. And this is d. So there's a problem with that. Okay, so it's barely a sketch, but so we have here a pretty decent understanding of the completion and how this works. And one of the applications of the coin structure theorem gives us well, it's one of the possible ways of proving this. There are several corollaries with this, but if I take a non-singular point, then its completion is going to be this coin structure theorem, and there, well, the argument would be a bit complicated to reproduce here, but what this implies is that then OX of A, and not completed, is a mu of D. So the idea is to find a technique that you can bring back down the product between the mu of D of the completion to the local ring. This is because the power series ring is a mu of D, and you can find an extra argument that brings it back down to the original ring. Okay. So UFD. So for those who maybe don't know, this is unique factorization domain. So this also brings you another ingredient, is that it is a domain, for instance, but also that it is a unique factorization, or factorial. Sometimes you find this terminology, factorial ring. And there is another characterization of factorial or UFDs, is that any fine ideal of height 1 is principal. So this might be, why is this interesting? Well, it has actually a geometric application. So I wanted just to add this important application. So I take a smooth variety x, right? And a rational morphism of x to a projective space. So, yeah, okay, let's call it phi. So, as you remember, phi is a morphism that is not necessarily defined everywhere, but only on an open subset of x. However, since x is smooth, all of its local rings are UFDs, and this amount, and this can actually gives us an information about the locus of indeterminacy. So, indeterminacy locus of phi. So the points where phi is not defined is closed and of codimension bigger than what I mentioned. Like that. Okay. So it's relatively small. You could say that like this, right? Okay. So let's take a quick project, let's say like this. Fine. Okay. So phi is given by homogeneous coordinates. So we have okay, we take the homogeneous coordinates of Pn right here with phi I, so it's a function defined from x to k. Sorry, it's a rational function defined from x k. Okay. Okay, a rational function. Okay. Okay, sorry, it's sometimes difficult to manage these proofs. Okay, so we are going to cover x by affine opens, right? And restrict phi I to xi ui, like this. Okay. And we have phi I restricted like this to it's the quotient of two functions, right? Because the fi's and ji's are going to be in a regular function over, let's say, xi, like this. Well, no, I gave another notation for this. This is ax, so this is the coordinate of ax. So rational functions, if you remember, they are quotients of two functions from the affine coordinate ring in this setting. So what I want to know is what's going to happen if I restrict it on this to the affine coordinates. So let's see. Okay, so we just need to show this, where it is, yeah. We just need to show this property locally around a non-singular point. So we need to show for an affine variety x, up to replacing x with its local charts, and then by considering the union, then the dimension won't vary. If all of these if the intersection of the locus, indeterminacy locus, with any of these open charts is closed and of codimension bigger than 2, then the whole thing will also be closed and of codimension bigger than 2. So this is what I wanted to reduce to. Okay.
How did we choose the cover? Was there anything specific about the cover? I'm a bit confused about the subscripts on the bottom.
Oh,
the UIs.
oh,
and the
sorry.
accents.
Yeah, sorry. Yeah. No. Yeah, I'm sorry. I tend to prefer the letter I to K sometimes. It's overused. Okay, so we have an affine variety. And since any local point we can find, we can multiply by a common denominator of the phi i's at OXA. So if I consider the elements phi I as elements of the fraction field of OX of A, then I can eliminate all the denominators. And also, I have a notion of GCD. Alright? And factor their GCD out. Now, the reason for this is quite simple, is that if I have phi 0 times a common element f, right? Okay, with f regular at A, then this will also be equal to phi by 1 by n because of how the homogeneous coordinates work. Like this. Alright. And a point x in this big variety, affine variety, is indeterminate. If and only if x is a common zero of these phi things. And I'm going to write it as y for this subset. Okay. So suppose by contradiction so this also proves in some indirectly that the locus of indeterminacy is closed. By contradiction, suppose that its y is of codimension 1. Okay, if it's codimension 0, then that would mean that it's nowhere defined. That's not interesting as a morphism phi. We suppose that it has points of where it is determined, where we have an dimension. So it's at least codimension 1. Okay. What happens if it is codimension 1? Well, let's look at the idea that this generates inside of the local ring OX of A. Then the prime idea is of height 1. Okay, so like this. Now, why is it prime? This is probably something I cheated. We can suppose that A that we reduce the fine chart as small as necessary, as we need, so that let's say there is only one irreducible component we are interested in, so that we are around only an irreducible, a single component, and choose A to this, an A around this irreducible component. So, so this variety Y could be something a little bit complex. Alright, so if I imagine curves inside of a surface, but you can choose an affine subset. Okay, so this is a affine chart. This, but also this, and finally this is a variety Y. And inside this affine chart where we have only one reducible component, you choose a point A. This is what. Okay. So this is why in this affine chart the ideal defined by IY is prime, and it is of codimension 1 by contradiction, so this will be height 1. So if it is height 1, since O except A is an UFD, then this is going to be a principal idea. So I wrote it down like G. Like this. But what is this G that we have here? G is going to be a common factor of the 5 i's. So G is a common factor of the fi's in OSA, which is a contradiction by what I just erased, supposing that the fi's are co-prime, because I factored out the GCD. Right? Because the 5i's are assumed co-prime. Okay. So why did I do all these efforts for this theorem? That looked a little bit confusing. Well, the argument is to see what happens if I want to look at birational morphisms between curves and surfaces. Right? So there are two very simple corollaries of this. Okay, so if I have set C a smooth curve, well, remember it's a variety, affine, projective, quasi-affine, quasi-projective, a smooth curve, and okay, then any birational morphism from C to a projective space, being projective is very important. I just erased the main ingredient, which was the factorization process. um, is a regular moment. Since the curve is smooth, then the codimension of the indeterminacy locus is bigger than 2, but that just means that there's nothing, because there's not enough room to have a codimension 2 subvariety in the curve. So what does this mean? Well, what happens if I take projective curves? Okay, so two projective smooth curves are.
Do you need Russian?
Oh no, sorry,
Rational.
rational. Yeah, sorry, no, I was thinking birational for the here. Birational. If and only if they are isomorphic. Oh, sorry. This was what I was trying to arrive at. Okay. So. Okay. So this is one of the main ideas I wanted to arrive here, is that the classification ends of curves. Amounts to finding a unique smooth model for them. So what is a model? It's a variety that is birational the original one. Okay. So if we find a birational model for smooth model, for a curve, then we know by this corollary here that it will be unique. Up to isomorphism, of course. Okay. So I wanted to insist a little bit about curves as a subsection of this chapter a little bit more, just to see to go into the structure of the logarithms of smooth curves a little bit further. So by the Cohen structure theorem, I abbreviate it like this, Cohen structure theorem, we know we have that the local ring is sandwiched between two well-known structures. So we have the power series rings in one variable on one side, and on the other side we have a polynomial ring localized at T. Okay? For any local parameter in OX.
Is this a regular point?
Oh yeah, we have a regular. Sorry. Implicitly, I was already thinking that the O is regular.
Andrei,
Yes.
do you allow me to make a comment before you move on?
Go ahead.
Go ahead. It's a historical comment.
Okay, yeah. Great.
So as you see in this part, Andrei brought these concepts of unique factorization domains, height 1 prime ideals that were generated by single element, by GCD. Yeah. These are all 19th century concepts that were developed by, well, let's mention Dedekind. He's a tag for the Fermat's last theorem.
Yeah.
And it's like 50, 60 years later, I think
Yeah, yeah.
Zariski was one of the first who realized that these same concepts can be used to characterize smoothness. It's a big property in geometry. So it's a remarkable connection, I would say.
Most of these concepts were developed by 19th century mathematicians. So we had Kummer, Dedekind, Weber, Krull. Krull was a lot. Krull developed a lot of these concepts, but it's Zariski that really saw that we could bring them together for singularity cases like this. Indeed. So all of these things are already something that was basically Zariski's doing. And Cohen, Isaac Cohen from the Cohen structure theorem, is a student of Zariski. This was actually a problem that was given to him by Zariski. Well, we will actually see a lot more stuff that we are used to in algebraic number theory just ahead, because we'll mention Dedekind rings and integral closure, the link with integral closure.
So, in the connection to curves, the second remark I wanted to ask, are you going to show how we factorize the nodes, the local ring of the nodes, how the equation of the node can be factorized in the completion as a product of two power series?
Oh, that!
I think this is an extremely important example that will help the equation of everyone. What's the difference between the local ring and its completion?
Okay, so let's try to make an example which gives a non-singular example. Yeah, indeed, that's a good idea. What happens if it is not smooth? If it is not smooth. So indeed, we're going to take. So this is a classic example which I should have mentioned indeed. What's going to happen to the completion if I take the node? So the node, recall, this is given by the equation y squared is equal to x squared times y plus x. So what happens in the localization here? Well, as you recall, we have two tangents here. Okay, so this is the cone of our singularity. And what happens to the local ring of this singular curve? So let's give this a name. Let's give it the name C. And so OC is not regular. And in fact, we can see that by looking at the completion, which is isomorphic to. So we know that OC, that C, 2 divided by its equation. Okay? And this equation actually, which was irreducible in the polynomial ring, becomes reducible. It's actually, you can actually factor it by a very interesting way. So y minus xy 1 plus x. This is a square. Okay, so this is a square, and this also is a square. We can't really see it, but in the power series rings, this becomes a square, because this is going to be x minus 1 plus x times y plus x square root of 1 plus x. And you know that 1 plus x square root is 1 plus half of x plus, I really don't remember about this, but usually it's an expression of the sorts 1 half k 2x to the k, like this. So this is the power expansion of the square root in the power series rings. So all these coefficients are going to be non-zero, so this is why you actually need to accept things. So this ring is not even, so this is not even a domain. Right? And you can also consider the Chinese remainder theorem and actually see that it's factorable as k over y, no, sorry, square x, it's rather like this. So, in some sense, the completion will give you formal functions on this, on locally around your variety, and it will be just, and it will reduce to seeing what happens in the code.
Yeah, so the completion really captures the very local behavior around the singular point.
Yeah.
And the very local behavior around the singular point, the singularity looks like just two lines intersecting at the origin.
Exactly.
This is what the completion gives you here. Yeah, right.
So, where you're on. Just a second. Go ahead. So there's a terminology for what we said, mentioned here, is that it is not analytically irreducible. So, well, it's we either mention the ring or the point. So, OCA, OC at A is not analytically irreducible. So, if we complete the local ring, we obtain something which is not a domain. There's also a notion of analytically reducible or reduced, which amounts to saying that the completion is a reduced ring. But sometimes this also cannot happen. Okay. Okay, so where was I? Oh yeah, the local structurings of smooth points in curves. Okay. So it's kind of a funny story because this, well, history-wise, because you are more acquainted with, and historically this is what happened as well, is that the algebra superseded the geometry in this particular area. Is that, okay, so for a regular point and any t in OX of a curve, sorry. The local parameter, any function inside of the function field, actually, there exists a unique integer n and unit inside of xa. So this just means that we are taking units. In the ring, such that f is equal to t to the power n times the unit. So if you ever did a little bit of algebraic number theory, this actually tells you that this is a discrete valuation ring. I'll mention and define discrete valuation rings just after that. Okay, so this is the first point. Sorry about this number. So, and I will have that f is going to be regular at the point A, if and only if this integer is positive. If it is positive, then all of these expression is positive, so no worries. And this n is called the order of f at A and is independent of T, the choice of the local path. Okay. So I'm just going to give you a couple of the steps of the proof, since I'm running out of time, and give you the rest as a simple verification of the rest of what remains to be done. Okay. So when f is irregular, then I will have that f of A is equal to 0 if and only if f is in the maximal ideal, which is generated by T. And this amounts to saying that T divides f in Ox of A. So what do we do? So we iteratively divide by T and obtain a chain of ideals. So we have inside of Ox of A. So we have f, which is included in f of T if f is equal to 0, which is also included in f divided by T squared if we have this, if the quotient is still 0 at A, and so on. So if f is infinitely divisible by T, then we have a strictly increasing chain of ideals, which is infinite. And this contradicts the Noetherianity of Ox of A. So this is stationary, meaning that at some point we won't be able to divide by T, since Ox of A is noetherian. Okay? So this proves the existence of M in the regular case. Okay. So we have f over T over N, which is equal to U, okay, in Ox of A. And U at A is not equal to 0, which amounts to saying that it is infinite. Okay. Step 2. F is not regular. So, how do we deal with it? Well, we know it's a quotient of two regular functions. So, I just take the two functions, which are regular inside of Ox of A. I apply step 1. So this is going to be equal to T to the power n1 minus n2 times u1 divided by u2. So this is also a unit inside of Ox of A. So okay, we did it for that one as well. What else? Okay, so the remaining ones, the remaining points, I leave as an exercise. It's very straightforward. So remains. So that would be step 3 and 4, the unicity of N and independence of T. So I did this exercise at home, it's not that difficult, I assure you. Okay. So what I wanted to say was that these types of rings have a specific name. They are called discrete valuation rings. Okay. A ring A is a discrete valuation ring there exists a map mu from extraction field, where we get rid of 0, to domain. I'm sorry. If there exists a map like this, such that we have two properties, so I already mentioned maybe this in my introduction. So we have the properties of being a valuation. So this is discrete valuation because the group to which it assigns values is Z. So this is, so okay, we have the property of, this is the multiplicativity and this is the return property. We'll come back to it next week. Okay, such that A is the set of positive values. Okay, so this is X in its fraction field, in its own fraction field, such that mu of X is positive, and we need the 0 as well. So this we will count on such things plenty of times in number theory. When we looked at local, local localizations of Z to look at number fields. Let's see, and we actually have a geometric example here, which are the local rings of smooth curves. So there is a very interesting way to characterize the DBRs. So I'm going to give a proper definition here. So fix, let's see, dimension 1, local ring. So M is the maximal ideal case there is a field. Then we have equivalent statements. This is just an abbreviation for the following are equivalent. So to go faster, A is a discrete variation ring if and only if M, the maximal ideal, is principal. Alright? Which is a very easy way. So A, the other characterization is that the ideal is regular. So if you recall, that means that the dimension of the square free members of the maximal ideal is 1. And the more interesting part is if A is integrally closed. This is the extra information we didn't have until now. So what is integrally closed? Well, a domain is integrally closed a domain, let's give it a name A, if for all x in extraction field A, if xn plus an was 1 x for some i's in A. So if x satisfies an integral equation, then x is in A. So there are no fractions beyond the elements of A that are integral over A. So this is what means to be integrally closed. Thus, if we combine everything we amounted here, that so A in X is smooth, we know that from this theorem that it amounts to saying that OX and A is regular. So this is what we did last time, and what we added today is the fact that it is going to be integrated. Like this.
Maybe it's a good idea to give a geometric interpretation of integral closed, like finite birational morphism. If there is a finite birational morphism X with Y being normal, or with this integral closure condition, then X is isomorphic to 1. Something like that.
Okay, so let's
just as a remark.
Yeah, but I need to define what finite is.
Finite fibers.
No, that's quasi-finite.
Ah,
that's
well,
quasi-finite.
Okay.
No, actually, finite morphism is defined by integrally closed stuff. Well, finite module.
Just as a
things, extensions.
Imprecise
okay.
motivation.
Geometric picture.
Yeah, because it's not clear where this equation comes from. What's the connection with the geometry?
Okay, so let's see, how could I introduce this? Okay, so take affine, and A of X is affine irreducible, right? Is integrally closed if and only if, let's say, for every y or x which is birational plus finite fibers is isomorphic to x. Okay? So the general picture is that we have x which is here below, and finite, these types of morphisms are some things that look like this. So we have a ramification, so if I have a point here, you have a finite number of points over it. So you take x and you kind of, how do you call this? Bend it above itself, like this. So this means that being integrally closed means that you can't really bend it in a way to obtain something like this.
Yeah, this finite condition translates into algebra into an equation of this form there. Yeah, and because the assumption that A of X is integrally closed, there is no such equation. So there are no twists like that.
Yeah.
So there is a isomorphic. Exactly. That's the intuition, the geometric intuition.
Yeah. There's another intuition that comes from analytic geometry, but it is a bit more complicated. It's supposed to generalize the Riemann extension property, but it's a rather difficult way to bring it to this intuition. Okay. So why am I talking about this all this? Is because I wanted to introduce the last concept, well, hopefully the last concept for this, that if you had some background with algebraic geometry, you know this. Okay, so let A be an Euclidean. So this time, just a ring. A domain, but not local, not necessarily local. Okay. Of dimension 1. Then we have the following. The following are equivalent. A is integrally closed. And all of its local ideals, localizations are DVRs. What does that mean? So, for every prime, the local rings, so what are these? These are x over s, or x is an element of A, and s is an element of A with I of p, is a DVR. So the remark I wanted to make about this is that, let's see, so an affine curve is smooth if and only if A of x is integrally closed. So for curves, we actually have an even stronger interpretation than this. We just know that the curve is smooth to begin. Like this. So let's see. Okay. Okay, so I'm gonna erase the notification. So we have a global equivalence for smoothness in the case of curves, which is this integrally closed condition. And okay, so there are a couple of so we have a very basic notion that comes along with this remark. It's that an affine variety is normal if A of x is integrally closed. So a general variety is normal if it is covered by affine normal varieties. Well, open subsets. So these open subsets will have a variety, an affine variety structure, and they are the. Okay, so for curves, being smooth is equivalent to being normal. So there's a bit of a confusion between the terminology of normal and integrally closed. There are some people who call these rings normal rings, but in most literature it's integrally closed. There's actually, for algebraic subsets which are not irreducible, there's a general notion of what it means to be normal, but I won't deal with that. So there we have an extended notion of what means to be normal, but I won't deal with that here. Okay. So, okay, let's give a couple of examples, or at least see a couple of examples. So, there's a general fact, okay, that says that an E of D is integrally closed. Okay.
It's an easy exercise.
Yeah, you just take an integral equation and you factor out the denominator and numerator of your possible fraction x, and then you use this. Use it all of the time in elementary number theory, this Eisenstein criterion of divisibility, but okay. So for instance, we have Z is integrally closed. All the rings are integrally closed. And also if I replace K by Z, we also have integrally closed thing. Okay, so I'll give you something, an example of something which is not integrally closed. And since we have this, I just erased this, so sorry about that. But since we have this characterization of smooth curves, I just need to take a singular curve, right? So, okay, so. Is not integrally closed. And to see that, you can actually, so it is a domain, since this is a reducible element of an UFD. So this is a domain, so we have the classes of x and y inside of this string are non-zero. So I can consider their fraction. So the element x or y is in the fraction field of A and not in A itself, but what happens if I take the square of this thing? Well, in the numerator I have y squared, x squared, but y squared is equal to something else based on the equation we have given it. So this is equal to x squared y plus x over x y squared. I can simplify the x's, so we have this A. So y over xy satisfies t squared minus 1 plus x, which is an integral equation, right? So you have explicitly a way to show that it is actually not integrally closed. Okay. I still have, let's say, 5 minutes. I'll give you an example of something which is a bit more complicated. And I'll finish with this, and next week we'll finally understand what the resolution of singularities mostly is about. Okay, so this, so example of a ring which is integrally closed, but not regular. Okay, so since we can't really look at curves, we need to look at surfaces. And indeed, we will have such a surface. We just need to look at a cone. The most simple thing you can imagine. Okay, so let's see. Okay, so I take this axis will be Z and this is X. Okay. So I'm going to take its coordinate ring. So I need 3 variables. So it's Z. Like this. And I'll call the elements that correspond to X, Y, and Z. I'm going to give them names. X bar, Y bar, Z bar. So I'm going to prove in the remaining time I have that it is integrally closed, but not regular. Okay, not regular you can see by the simple Jacobian criterion. Right? It is the gradient is 0 at 0, so it's a non-simple. Okay. But how do you prove the fact that it is integrally closed? Well, you need to know a little bit about how these things.
10 more minutes.
Okay. Okay. So as you can see, I've written this equation in a special form because I wanted to express it as an equation of z in terms of x and y. So you can imagine this is exactly what I wanted to show. Is that this is something where the base string is k, is y. I add a variable and I divide by this equation z squared. Okay? And this is an algebraic reducible equation. Okay, so I didn't specify, but I wanted the characteristic to be different than 0. Otherwise, this is
You can factor.
Okay, so the fraction field of A, while you will have kx of y inside of it, but also you just need to divide by, you just need to add the variable z, which satisfies this property here. So this is going to be like this, because once when you add an algebraic element to a field from an extra big field, it still remains a field. It's okay. So we have the structures of these elements, okay, and we just need to show the following thing. So any so if I take an element from the fraction field, it will show up like this. So it will have coefficient element u and v. Well, this is v, like this. That is integral over A, has a minimal polynomial which is minimal polynomial, which is integral, meaning that its coefficients are in A, and its minimal polynomial is going to look as follows. So you remember, maybe you remember the trace and norm of a polynomial. So the trace is going to be 2 of u, and the norm is going to be something a little bit more complicated. V squared, like this. So 2u is going to be A. We assume that the characteristic is different from 2, so this means that u is inside of k of xy. So we have the second part, the second part here. This product here is going to be also in the ring, but this can be factored. So these are co-prime irreducible fractals. Okay, still again because the characteristic is different from 0. But this implies that V is also in A, which implies that V is in xy. Okay? Now why is that? Well, simply put, that means it's because if V would have some denominators, the denominators would only be x, one of these two, but then elevated to the square, it would be too much. So, okay. So the conclusion is that U plus V Z is in action A, which concludes the proof that this string is integrally closed. Okay, so it was a bit of a rush, but finally, yeah. Next time we're going to start to actually try to formulate the problem of resolution of singularities, and I will give you the resolution of singularities of curves via normalization. Since we have this integral closure condition, what we need is to take the integral closure of its coordinate ring, and this will actually give us another variety that will be our sought after resolution of singularities for curves. Okay, so I'll stop here.
Okay, so let me make an announcement. Next meeting of the course will take place next Monday.
Okay.
Here, same time, 1:30.